Hello students, in this video I will be talking about more on shapes of functions. So just to recap, in this lesson series we've talked about what it means for an equation to be a function and when an inverse will exist or not, and it has a lot to do with the overall shape of the function, whether or not the function is one-to-one or whether or not the function passes the vertical and horizontal line test. So this video I'm going to spend a little more time just talking about, again, some generalities, okay, that we can make about functions, and it has to do with function symmetry. Okay, so let's take a look. So functions can have symmetrical properties. Okay, it can have line symmetry as well as point symmetry. So rather than talking about line symmetry anywhere on the in the coordinate grid, we're going to focus on just one very special line, and that is symmetrical over the y-axis. And rather than talking about symmetry over any particular point on the coordinate grid, we're going to focus on one particular point only, one very special point. Guess what that is? That's the origin, right? So if functions appear to be symmetrical over the y-axis, this is actually classified as being an even function. And if functions are classified as being symmetrical over the origin, or in other words, having this rotational symmetry, 180 degree rotational symmetry, it's classified as being an odd function. So this is nice and all, right? There's actually a way for us to algebraically test whether or not a function is even or odd, whether or not it has whether or not it is symmetrical over the y-axis or whether or not it is symmetrical over the origin. And the way in which we test is given by this relationship here. And what is meant by this? Well, if I take any point, any positive value of x, okay, and evaluate the function, and if I take the same exact value on the other side, right, the negative value of that same x coordinate, what I should end up with is the same exact y coordinate. That's what this test is saying. So visually, how does that look? Whoops. This is saying that this point over here, which was at a comma f of a, if I'm calling this f of x here, then over here, okay, you see how it's the mirror image, right? At the same x coordinate but negative, yes, technically I should evaluate f of negative a, but it evaluates to f of a. It's the same exact y coordinate. So that's what this is saying. And algebraically, okay, this has to be true. Let's say if I call this b and this is f of b, then what's true is on this side over here, negative b, it has to be f of b as well. So that's what it means algebraically, okay, for a function to be even. Now, how do we test whether a function is odd? Well, a function is odd, okay, when it has that rotational symmetry over the origin. That is what I've said. But algebraically, we can test this by doing something similar. So if I evaluate this, okay, let's say at a, and this evaluates to f of a, then the negative x coordinate, when I evaluate it in the within the function, yes, it's f of negative a, but it should evaluate to the negative value of that y coordinate. Okay, so let's see how this actually works. Okay, so what we're going to do, okay, if you're asked to prove if the following functions are even or odd, what you're really doing here, okay, translation, what the instruction is really asking you to show is whether or not it has that vertical line symmetry or that point symmetry. Okay, show symmetry over over y-axis or origin. That's what it's asking you to do. If a question is asking you to show or prove if a function is even or odd, right? That's how that's what it's really asking you to do. It's not asking whether or not the function is an odd degree equation or an even degree equation. No, it's not asking that, okay? But it's really asking for the symmetry. So let's take a look. How can we show this? So according to what I showed you in a previous slide over here, right, to test whether or not we have an even function or an odd function, we need to substitute in the negative values of x and see if it actually changes, right? So that's what I'm going to do. So I have this function right here. I'm calling that a of x, and a of x is equal to x cubed plus x. So right now, x here, okay, I'm declaring that these x values are positive. So what I'm going to do is I'm going to substitute in x values that are negative. And if I do, I'll end up with an equation like this. Wherever I see x, I'm replacing it with negative x. And if I proceed to rewrite this, to simplify this, get rid of the parentheses, I'll end up with a of negative x is equal to negative x cubed minus x. Look at this closely. What's a relationship between this end result and what we started with? That's right. This is the negative form of what we had started with. So wait a second. If a of negative x is equal to negative a of x, where have we seen that? This is proof that the function that we're dealing with is odd. In other words, okay, whatever x coordinate we throw in, okay, if it's negative, then it will be the negative of the y coordinate when evaluated using a positive x value. If what I said there was a little confusing, right? What you need to understand is odd simply means we have a function that is symmetrical over the origin. That's all that's saying. And when you graph this function in a graphing calculator, this is the picture that you get. And you can see clearly that we have rotational symmetry. We have that point symmetry over the origin. Okay? All right, let's take a look at another one. So I have b of x. b of x is equal to radical x squared plus 1. Again, the way in which we prove whether or not a function that we're dealing with is even or odd is by substituting a negative x coordinate in there. So that's what we're going to do. And we're going to do a little bit of simplifying, right? Let's remove the parentheses. So this becomes, again, square root of x squared plus 1. Because if I square the negative x, isn't this what I end up with, right? And if you examine this function the way it is compared to the original, what do you see? You see that b of negative x is in fact the same as b of x. So what can we conclude about the function b of x? Well, the conclusion is b of x must be even. So what does that mean? The function is even, so therefore it will be symmetrical over the y-axis. And if you graph b of x in the graphing calculator, and I encourage you to go and do that, you're going to end up with a graph that looks like this. And indeed, this function is symmetrical over the y-axis. All right, moving on. So I have c of x is equal to 2x plus 1. Again, the same attempt, c of negative x. And I am going to remove the parentheses and try to rewrite this and determine whether or not c of negative x has any relationship with c of x. And I look at this, right? Negative x, don't mind this right now. I look at this, okay? C of negative x is equal to negative 2x plus 1. Is this in any way related to c of x? I mean, it looks similar, doesn't it? It has like the negative slope value. The the negative of what the original slope value was, and it has the same y-intercept, it looks fairly close, doesn't it? No. So in order to show whether or not the function is even or odd, it has to be like the negative of the original, or it has to look exactly like the original. Because it doesn't look exactly like the original, and it doesn't look like the negation of the original, it is not equal to the original at all, right? So because of this, this is neither. And we all know how the 2x plus 1 looks when graphed. It's just a straight line with a y-intercept of 1 and the slope of positive 2. So it looks something like that. And you can see there is no line symmetry and there is no point symmetry over the origin. All right, let's take a look at another set of examples over here. Pause the video to see if you can figure this out. D of x is equal to x squared plus x. So in order for me to test whether or not this is odd or even, I replace x with negative x. And I attempt to rewrite this. So negative x when squared becomes positive x squared. And negative x, when I remove that, that becomes a subtraction. Is this in any way related to the original? Is d of negative x the negation of d of x? Or is it exactly like d of x? It's actually neither. So because of this, this will have no line symmetry over the y-axis, and it will have no point symmetry over the origin. However, recognizing that this is a quadratic equation, right? It does have line symmetry. So despite it having line symmetry, it does not have line symmetry over the origin. Over the y-axis. Because of this, we still call this, it's neither. Okay? And again, when someone's asking you to state whether or not a function is even or odd, what they're really asking you to do is to explain whether or not the function is symmetrical over the y-axis or symmetrical over the origin. Mathematicians are very lazy people. They like to say things in the most succinct manner possible, succinct and efficient manner possible. So rather than saying symmetrical over the y-axis or symmetrical over the origin, they just say odd or even, right? All right, so moving on. I have e of x is equal to x squared minus 1. What I want to do again, I want to evaluate this thing at negative x. Remove the parentheses there. I end up with x squared minus 1. And this, in fact, looks exactly like the original. Because of this, this is even. And we already kind of knew this, okay, walking into the problem, because we are really familiar with graphing quadratic equations at this point. And this particular quadratic equation will have the axis symmetry at 0, which is the y-axis. So yeah, this is going to be even. All right, next one here. This is also the last question. I want f of x, or to show whether or not this is even or odd. This looks pretty complicated, doesn't it? Well, we do this all the same way. Wherever we see x, we replace it with negative x, and then we're going to remove the parentheses. We'll end up with negative x over x squared plus 1, because when negative x squared, it just becomes just regular x squared. So is f of negative x in any way related to f of x? Actually, it is. It is negative f of x, right? If I pop a negative sign in front here, that's what I'll end up with, right? So it is equal to f of negative f of x, and this is going to be an odd function. And when you graph this on a graphing calculator, what's the shape of it? It's going to look something like this.